Okay, so this is the third video. What we discussed in the first two videos were the SN2 reaction. So to summarize those conditions that favor an SN2 reaction, the best conditions are to have a substrate that is unhindered in the back of the alkyl halide bond. So the methyl alkyl halide is more reactive or reacts quicker than the primary alkyl halides, and then secondary are the slowest. Remember, tertiary alkyl halides do not react. They're too bulky for the SN2 mechanism. The next thing we said we need is a strong or a good nucleophile. That's a better word. You want a nucleophile that's negative. The atom that contains the negative charge to be less electronegative, and you want it to be a larger atom if possible so it's more polarizable. So the ones from the good list and moderate list, we had the sulfides, the cyanides, the iodides, the oxides in the series. So you can go back over those. And then the other thing we talked about is the solvent for the reaction. We said we want a polar aprotic solvent like DMSO, DMF, or acetone. Something that stabilizes the charged transition state, but it's not protic or has any acidic hydrogens, any hydrogens attached to electronegative atoms. That will favor another reaction. And then I added one here, the leaving group. I almost forgot. We want a leaving group that will leave quickly, that can stabilize the negative charge forming in the transition state, lower the activation energy, and something that's stable as it leaves the molecule. So the weak bases are best. So for the halogen series, iodide is the best leaving group and fluoride is the worst. Now we're going to talk about an SN1 reaction, the other types of substitution reaction. Remember, the 1 refers to the kinetics of this nucleophilic substitution. 1 means unimolecular, which means in the transition states, or not the rate transition state, in the rate determining step of the reaction, there'll be more than one step. But in that rate determining step, the slowest step, there's only one molecule involved in the kinetics of that the reaction. So it's unimolecular. So let's look at an example here of an SN1 reaction. Here we have an alkyl halide. Now notice this alkyl halide. The carbon attached to the halide is substituted with 3 methyl groups, 3 R groups. Therefore, we have a tertiary alkyl halide. Now, what we said in the SN2 video is that tertiaries are too bulky to undergo SN2. So what we see here is that we have an alkyl halide that will not react under SN2. This is an SN1 reaction. Now, if we wanted a really strong nucleophile for an SN2, we want a moderate to weak nucleophile for an SN1 reaction. It will favor SN1. So instead of up here we have the alkoxides, good nucleophiles for SN2, we're going to use a moderate nucleophile. This is the protonated version of an alkoxide. It's an alcohol. An alcohol has no negative charge, so it's a moderate nucleophile. It's a weak nucleophile. So notice the solvent we have here. The solvent is polar, it's an alcohol, but notice that there's a hydrogen attached to the oxygen. It's polar and protic. It's got a proton, a hydrogen attached to that electronegative oxygen. So we have a different type of solvent too. Polar protic, not polar aprotic. So everything in this reaction screams, I'm not an SN2 reaction. And in fact it isn't. This is an SN1 reaction. The product of this reaction, the halide is still the leaving group, and now the nucleophile, which isn't negative, it's not negative because it's got a hydrogen attached. But the nucleophile that will be doing the substituting, the hydrogen will not end up on the product. So for the methanol, it's the protonated version of the negative nucleophile. The methoxy OCH3 group will be substituting the bromide. And the hydrogen will leave with the bromide to form the acid. So our product here we have T-butyl bromide. It will instead be the T-butyl group, there's that reactive carbon, and now it will be bonded to the OCH3 of the nucleophile. Okay? And our byproduct, as the bromide leaves, takes the hydrogen proton with it, and we get HBr as our byproduct. So see that the methoxy group substituted the bromine, and the bromine, the leaving group, is now bonded to hydrogen. This is an SN1 reaction. It doesn't occur in one step. It doesn't occur by an inversion of stereochemistry. It's going to be a different mechanism, which we'll look at. Okay, first I want to actually draw your attention. If we were going to look at the mechanism of this reaction, let's look at the energy diagram, the reaction diagram. And what we see is that for the SN2 reaction, the diagram went from reactants to products, and there was one transition state. However, in the SN1 reaction diagram, we see that there's two transition states. The number of transition states equals the number of steps in the reaction. So we have transition state 1 and transition state 2. So this is a two-step reaction of an alkyl halide with a nucleophile. So let's look at the mechanism now. The mechanism starts with the alkyl halide alone, and this is the rate-determining step. Because the nucleophile cannot get in the backside of the tertiary alkyl halide, it's too bulky in the back for the nucleophile to get in. The nucleophile does not start the reaction. Instead, the alkyl halide being heated has to break the alkyl halide bond first. So the CX bond will break, and we'll end up forming a carbocation intermediate as the bromide leaves. So this is the slowest step because it forms a carbon that is electron deficient. Remember, carbocations are planar, and they're cationic because they have an empty p orbital. They do not have a full octet. So we go through a planar transition state of the carbocation here. Now, from that carbocation, now any nucleophile can react. It's planar, it's open. So now the nucleophile can quickly come in to satisfy the octet of the carbon, and the oxygen, the weak nucleophile, will bond. Now, when methanol, our nucleophile, bonds here, the hydrogen's still attached. So the oxygen has a formal positive charge at this point. It's the protonated product still, because the hydrogen's still on. So the last step of the reaction will just be deprotonation. And this occurs very quickly. The bromide or the methanol, any weak base, can deprotonate that strong acid, and we get to our final product. Now, technically, the substitution part of the reaction are just the first two steps. The third step is a neutralization because we're forming the neutral compound. Alright, so I guess I should put a 3 there. Now we've formed the ether. We've substituted the bromide for the OCH3 and HBr as our side product. Let's go through the mechanism again. The substitution part of the mechanism to get the bromide substituted for the nucleophile takes 2 steps. And then the final step is this neutralization to form a neutral compound. So do we remember the reaction mechanism? Alright, the first step of an SN1 mechanism, when you have a tertiary alkyl halide, you cannot do an SN2. The first step is dissociation of the halide. The halide dissociates, forming the carbocation intermediate, and bromide goes away as the leaving group. So dissociation of the halide to form the carbocation intermediate. Now the nucleophile, the weak nucleophile, attacks, and we get the nucleophile added to the carbocation. This is the substituted product, but then bromide is a weak base, but the protonated ether is a strong acid. So we deprotonate and get down to the neutral form. The OCH3 and the byproduct is HBr. Alright, so the substitution takes 2 steps, and then there's a neutralization. It goes through a planar carbocation intermediate. Now, all of these things that we're talking about in the mechanism will be important when we go to talk about the characteristics of this reaction. Alright, so looking at the mechanism, we can describe some different characteristics of SN1 versus SN2. The first is the kinetics. Notice that there's more than one step here. And the first step of the reaction we said was the rate determining step. And in the rate determining step, the slow step forming the carbocation, all you have is dissociation of the alkyl halide. One reactive starting material will dissociate to form the carbocation intermediate. So in that step, the nucleophile is not involved. So when we look at the rate of the rate determining step reaction, it equals the rate constant K times the concentration of only the alkyl halide. This is important. If we doubled the concentration of the alkyl halide, we double the rate of the reaction for an SN1. If we double the concentration of the nucleophile, it will have no effect on the overall rate of the reaction because the nucleophile is not involved in the rate determining step. This is different than the SN2 mechanism. Remember the SN2 mechanism, the rate equation for the slowest and only step is K times Rx times nucleophile concentration. The rate depended on both the alkyl halide and the nucleophile. So if I doubled the concentration of the alkyl halide, I double the rate of the reaction. If I double the concentration of the nucleophile for SN2, it also doubles the rate of reaction where it didn't for the SN1. So we see that we can actually do kinetic studies with wet chemistry and we can determine whether a mechanism is an SN1 or an SN2 mechanism for substitution by changing the concentration of the nucleophile. If it has an effect on the rate, it's an SN2. If there's no effect on the rate, it's because it's an SN1 and only the alkyl halide is involved in the rate determining step. For example, here's an SN1 reaction. We've got a tertiary alkyl halide. Notice this carbon has 3 methyl groups attached, so it's a tertiary. And we're reacting it with sodium azide. The azide is the nucleophile, and either one of those nitrogens is fine. But the nucleophile is going to come in, and it's going to displace the bromide, and we're going to get N3 substituting the bromide. Now, it doesn't happen in one step. It's not SN2. Why? Because we have a tertiary alkyl halide, and we can't do SN2s with bulky R groups. So instead, what happens? Remember, in the rate determining step, only the halide dissociates to form the carbocation intermediate. So once this is gone, we end up forming the carbocation in its place. And now the nucleophile comes in and reacts, all right, the azide, in order to substitute. So we get a 2-step reaction there. All right, now, in the rate determining step, which is the first step, it's the dissociation of the alkyl halide. So the rate equation for this substitution is K times the concentration of our T-butyl bromide, the alkyl halide. What else does the mechanism tell us about the SN1 reaction? Well, we see in the rate determining step, it's dissociation of our leaving group, the halide. So just as before with the SN2, we want a good leaving group that's able to form a stable anion and dissociate quickly from our carbon electrophilic atom. So the same trend for leaving group in Rx applies with SN2 as it does for SN1. Iodide is the weakest base, the most stable anion, so it will dissociate the quickest. The slowest dissociating will be fluoride because it's a very unstable anion. Okay. All right. The other thing that influences the rate of the SN1 reaction is the substrate or the reactivity of the alkyl halide. So remember that in this reaction, we form a carbocation intermediate. So if we want the dissociation, the first step of the reaction, where the alkyl halide dissociates in the rate determining step to form the carbocation and the separated halide, we already talked about the leaving group. The reaction will go faster not only if the anion is more stable, but if the carbocation is more stable. So The quickest reactions for SN1 will be the ones that form the most stable carbocation once the halide dissociates. Now, we talked about stability being with two different effects, hyperconjugation for our regular carbons, and then we also have resonance stabilization as well. Resonance stabilization is usually, these are two different topics, okay? So for resonance stabilization, we have two types of cations that can form once the halide leaves that are resonance stabilized. Go back to chapter 7 if you don't remember these, but we can form if the halide leaves, we can form a carbocation, benzylic, or next door to a benzene ring, or we can also form a resonance stabilized carbocation, allylic, or next door to an alkene. So we have allylic and benzylic carbocations. Now, allylic carbocations have two resonance structures, contributing structures, while benzylic, back in chapter 7, have 4 resonance contributing structures. So for resonance stabilization, benzylic carbocations, if you're comparing a secondary benzylic with a secondary allylic or a primary benzylic with a primary allylic, the benzylic is always more stable because it's more delocalized as a cation than the allylic. Okay, what if you're not comparing benzylic or allylic cations? Remember our carbocation stability trend for our regular sp2 carbocations. If the halide dissociates from any of these, we end up forming the sp2 hybridized carbocation in the rate determining step. So which carbocation, due to hyperconjugation, is the most stable? It's the carbocation that has the most R groups bonded to it. So tertiary, go back to chapter 3 or 4 if you don't remember this, but tertiary carbocations are more stable than secondary, and secondary methyl, or primary, and methyls are the least stable. They don't exist at all. The most stable are secondary and tertiaries. We generally, for SN1 reactions, don't form primary or methyl carbocations. That would have come from a primary or a methyl alkyl halide, and those usually undergo SN2 reactions. So, remember that these groups usually always go SN2. Tertiary cannot go SN2, it always goes SN1. And then the alkyl halide that's secondary, because secondary carbocations are somewhat stabilized hyperconjugation, can do SN1s or SN2 reactions. So the secondaries, the 2s, can do 2 reactions. Methyls and primaries, those are unstable carbocations, so they usually don't go by SN1, they usually do an SN2 reaction. Alright, so we have 2 different trends for stability of the carbocation. If you're going SN1, you want a stable carbocation. Alright, so for our leaving groups, in order to, in the rate determining step, form that carbocation intermediate quickly by dissociation of the alkyl halide, the halide, when it leaves, has to be stable. Once again, the leaving group needs to be a stable, weak base. So for the halide series, just like the SN2s, iodide is the best leaving group. It's the most stable, followed by bromide, then chloride, then fluoride, which is the worst, slowest leaving group because it's not a stable anion. The next thing we want to look at is the substrate reactivity of Rx. In the rate determining step of the SN1 reaction, when the halide dissociates, remember it forms a carbocation intermediate. Rx dissociates in the rate determining step to form the carbocation plus the halide. It makes sense that if the reaction goes faster, that means the halide has to be stable, then so does the carbocation. So we want to form stable carbocations. There are 2 classifications of stable carbocations. What can stabilize a carbocation? Well, the one we talked about first in class was hyperconjugation. Back in the alkene chapter, we said the more R groups attached to a carbocation, the more stable it is. So if you have a tertiary alkyl halide, when the halide dissociates or moves away, you form that carbocation in its spot. So tertiary alkyl halides form tertiary carbocations. And we know tertiary carbocations are more stable, or the most stable or most hyperconjugated. The least are methyl groups. And primaries are not very stable either. So for SN1 reactions, tertiary and secondary carbocations are favored from secondary and tertiary alkyl halides. The other thing we said, and this is a separate thing, that can also stabilize a carbocation, in Chapter 7 we talked about resonance of ions. If you have an ion resonance, you have delocalization through the pi bond structure. There are two types of ways you can resonate an ion or stabilize it, the resonance. When that ion is created in a benzylic position or an allylic position. So notice here we have a benzylic halide. The halide attached, when it dissociates at that position, will form a carbocation. And once that carbocation forms, it's benzylic. It's stabilized. There's 4 contributing structures. Benzylics are the most stable by resonance. And then allylics. If you have an allylic alkyl halide, when that halide displaces, you make the allylic, or next door to the alkene, cation. And it has 2 resonance structures. So allylic is a little less stable than benzylic because it has less resonance structures. But overall, both of these are ways that you can stabilize a carbocation. So if you were comparing stabilities here, resonance versus hyperconjugation, if you had a secondary carbocation versus a secondary benzylic carbocation, the benzylic has not only the hyperconjugation that's the same, but it also has resonance. So that would be more stable. Now, talking about tertiary versus secondary versus primary versus methyl alkyl halides. Remember, over here, that SN1 reactions favor methyl and primary, SN2 reactions favor methyl and primary alkyl halides. But SN2 reactions can also do secondaries. Well, it turns out SN1 reactions, because SN2s do not do tertiary alkyl halides, SN1 reactions are favored with alkyl halides. But because secondary carbocations are also stable, you can get SN1 reactions for secondaries as well. So what I'm trying to say here is that the alkyl halide can determine which route, can be one of the factors that determine which route the reaction undergoes. If you have a primary or methyl alkyl halide, it will always undergo an SN2, most likely. If you have a tertiary alkyl halide, it will most likely always do an SN1. But if you have a secondary alkyl halide, it can do either SN2 or SN1. So you have to look at other factors such as leaving group, solvent, nucleophile strength. What are other factors that influence an SN1 reaction versus an SN2? Well, remember in an SN2 reaction, the nucleophile, which was the reagent, would need to be a good, strong, negative, polarizable, less electronegative nucleophile. Well, the opposite is true here. Not a good nucleophile, that will promote SN2. A weak or poor nucleophile will promote SN1. So we want weak or poor nucleophiles for these reactions. These are not negative nucleophiles. These are neutral nucleophiles, like water, alcohols, thiols, the sulfur version of an alcohol, carboxylic acids. Notice none of these have negative charge. Most of them are oxygens, but these are your poor nucleophiles. The last thing is the solvents. For an SN2 reaction, we wanted a polar aprotic solvent, but we want a nice protic solvent for this. So alcohols and water are the best solvents. And the polar A products are very slow reactions. So you want a polar protic solvent for these reactions.